In this lesson, we're going to continue our discussion of big idea number 2. So how does bonding and intermolecular forces affect the properties of a substance? And finish off learning target number 5. So by the end of the lesson, you should be able to describe the difference between atomic, molecular, both polar and nonpolar compounds, ionic, metallic, and network solids. And you should also be able to predict the properties based on the structure of the compound and the intermolecular forces it possesses. There are 6 types of solids that we're going to cover in this course, and they're all crystalline solids. Crystalline solids have the particles arranged in organized patterns. There are different ways that you can pack particles into crystalline solids. Check out the 2 animations on simple packing and close packing. The strength of the force holding the particles together creates the unique physical properties of that type of solid. So remember from our last lesson, if we're talking about the force between 2 particles, the stronger it is means we'll have a higher melting point and it will be harder. If we're talking about the force between the particle we're interested in and water, the stronger it is means the more soluble that compound is in water. And finally, something new we'll talk about today is conductivity. If the compound has charges, and 2, if they can move. Those are the 2 questions you're going to ask. If you say yes to both of those questions, then the compound will conduct electricity as a solid. So the first crystalline solid we'll talk about are known as atomic solids. Now, atomic solids are made up of individual noble gas atoms attracting each other. So let's draw 4 neons. Now, to figure out the properties of an atomic solid, we look at what intermolecular force are holding those neons together. Because they're atoms and they don't have any charges on them, then they will be attracted to each other in this lattice only by London dispersion forces. Now, how strong are those Londons? Remember, London dispersion forces increase with size. Because I'm just using tiny atoms, then the London dispersion forces are very weak. Because I have very weak forces, then my melting point is going to be extremely low. Now the melting point for a typical atomic solid is around minus 200 degrees Celsius. That's very cold. Also, because I have very weak London dispersion forces, my solid, when it is a solid, is going to be very soft. For conductivity, ask yourself these 2 questions. Do I have charges? The answer is no. So, atomic solids are non-conductive. If the structure had charges, would they be able to move? If you answer yes to both those questions, then you have a conductive solid. In terms of solubility in water, we got to talk about what force can be formed between a neon particle and a water molecule. Now, water molecules are polar with slightly positive H's and slightly negative oxygens. And because neon has no charges, it's nonpolar, and the only force that I can make between polar water and nonpolar neon would be a dipole-induced dipole. And because this is a weak force, then solid neon will not be very soluble. Our next type of solid is a nonpolar molecular solid. It's made by stacking nonpolar molecules next to each other. We can represent those nonpolar building blocks as bars. Because these are nonpolar compounds, the intermolecular force that's going to hold them in the crystal are going to be London dispersion forces. Now, because the molecules are bigger than the atoms we used in solid neon, these London dispersion forces are going to be stronger. But London dispersion forces are fairly weak. So that means in terms of melting point, all nonpolar molecular solids have low melting points. Now there's a big range depending on what size of building block you use. It could be pretty low, like CO2, where it's a gas at room temperature, or it could be like candle wax with 40 carbons in it, fairly large molecule, so that it's solid at room temperature. In terms of hardness, because we're using a weak London dispersion force, our solid is going to be soft. In terms of conductivity, I don't have any charges, so this type of solid is going to be non-conductive. And solubility in water, again, I can only create weak dipole-induced dipole. Therefore, nonpolar molecular solids have low solubility, which means not very much is going to dissolve in water. Number 3, polar molecular solids. They're made by stacking polar molecules so that their slight opposite charges attract each other. We can represent these building blocks by drawing bars again. But these bars will have slight positives and slight negative charges on them that will be in opposite orientation so that they will attract each other. So the attractive force that we're going to have here are going to be dipole-dipole attractions. And if we have the right combination of atoms and bonds, we could also use hydrogen bonding. So in terms of melting point, we're using medium kind of strength intermolecular forces. So that means our melting point is going to be medium kind of temperatures. So if you think of water, water is bound together with a hydrogen bond, and it melts at 0, boils at 100. So we're kind of medium temperature. In terms of hardness, we're going to be hard to semi-hard. Again, depending on the strength of the force. In terms of conductivity, do I have charges? The answer is yes, I have slight charges on my structure. But question 2, can my charges move? Well, when these particles are locked into the crystal, no, the charges can't move. So therefore, they're non-conductive as a solid. Will polar molecular solids dissolve in water? And the answer is yes. Because they have slight charges on it, they can be attracted to the slight charges on the water. Again, I could either use a dipole-dipole attraction, or if I have the right combination, I could use hydrogen bond between my water and my polar molecular solid, so then therefore they are soluble. Now, if that polar molecular solid dissolves in water, will it be conductive? When you dissolve something in water, you break the intermolecular forces between your building blocks. So each bar could then freely move. Would this create enough conductivity? Well, because it's only slight charges, it still won't be very conductive. Now let's have a look at metallic solids. The diagram for the metallic solid is included. This is the free electron model that we discussed in the types of chemical bonds note, where we have fixed cations in the crystal lattice that are held together by this free delocalized electron C. Now the attractive force that holds this crystal together is the full charge attraction between each cation and the free electron C, which is known as a metallic bond. Metallic bonds range in their strength, but they are fairly strong attractions. So because I have a strong attraction, the melting point is going to be high. Now, metallic bonds, because they range in strength, you get solid metals that are semi-hard to hard. It could be hard like iron, so a solid bar of iron is, or it could be semi-hard like sodium. Solid sodium is soft enough that you can actually cut it with a plastic picnic knife. Remember, the strength of the bond depends on the size of the cation and also how many free electrons there are in the C. In terms of conductivity, do I have charges? Yes. Can they move? Yes. Remember, the electrons are delocalized. They can move anywhere they want through the crevices and channels in the crystal. That makes metals conductive when they're solids. In terms of solubility in water, we have to attract one of these cations to a slightly negative oxygen on a water molecule in order for this metal to dissolve. Now, let's compare what's holding it. Here, I have a fully charged slight charge attraction, so that will be an ion dipole attraction. And then here I have a full charge attraction. And it's not just full charge. This cation here is attracted to multiple electrons in that free electron C. Remember the analogy of a metallic solid being a Rice Krispie square. You have that negative electron marshmallow holding those Rice Krispie squares in position. That's pretty tough to overcome, even for an ion dipole attraction. So water will not dissolve metals.